Thanks everyone for joining. Hi, this is Jayanta, and we'll be talking about modeling virtual epidemics to fight the real ones. Yeah, at this point, it has been like 15, 16 months journey, right? All of us have been through a tough time. I hope everyone is safe and doing well. But what we have been experiencing in the last 15, 16 months is too difficult even to digest right now. Over this past number of months, what all of us have been going through, we are heavily trying to analyze, understand what it is happening, right from our local neighborhood to at a global scale. So we are referring to newspapers, we are reading the news, we are going on TV, we are following people on Twitter, then going to YouTube, trying to understand what it is happening. There are a bunch of folks outside who are doing certain analysis. Some of them are coming up with some data, and then everyone is trying to make sense of what it is going to, what is happening, and how the future is shaped, or how future can be changed. So we have this specific discipline which is called as epidemiology. We have been following a lot many epidemiologists in recent past, and these are the people who are actually working on ground. They are working on wall footing for last multiple months. They are trying to understand data, and it's not just understanding, but they are the ones who are actually collecting the data. Like from collecting data, then they are understanding it, they are presenting it in a way that policymakers can understand and they can take certain actions. They're even working with labs, trying to understand if virus has been going under mutation, which is the age group which has most impact of the virus, what we can do to change this. And they have multiple tools with them, right? They are conducting surveys. They have dry labs. They have wet labs. Even some point in time, we would have heard about zero surveys. So these surveys are typically conducted to understand if we have reached the herd immunity or not. So all of these things they do come under the bucket of epidemiology. But none of us here potentially are epidemiologists. All of us are into software, and most of us are computer scientists. So basically, what we are doing with such a discipline, right? Maybe we'll be talking about it soon. But let's first try and understand how epidemic, or in this case, a pandemic works, and if we put it on a time scale, what it looks like. So right now we are at the stage, right, which is control and mitigation. The virus has already been amplified. It has almost traveled the entire globe. And then there's a second wave. People are predicting about third waves. Sooner or later, we'll get into the third phase, which is elimination. But once the virus has been eliminated, we still need to be prepared. So basically, that is where the first phase comes, which is anticipation. Anticipation followed by early detection, then containment. If possible, stop the spread right at the start. If we can do it, then we will not be struck with another epidemic or pandemic. So actually, this entire spectrum is a continuous ongoing process. And we have to repeat it. Even though we eliminate one virus, we do not know there are 100,000, quite an astronomical number of viruses present out there, and we still need to prepare for the next set of viruses and next pandemics and epidemics and so on. Basically, an epidemic is a complex contagion. So when I say it's a complex phenomenon, let me briefly talk about what a complex system is. And then let's see how epidemic becomes complex to understand. So basically any complex system, right, it has majorly four different characteristics. Aristotle, the quote has been famously said by Aristotle, but we are not sure who came up with this. It says the whole is more than sum of its parts. So basically what we are saying, we see a bicycle, which is quite a simple machine. So if we see, but can we say bicycle is made of tires, and then can we say or wheels, but wheel is not a bicycle. Bicycle has a brake, but brake is not a bicycle. Bicycle has its own entity. So if we look at these things into isolation, it doesn't make sense. But only when we put all of these things together, and then there are 100 such number of things which come together to build one such system. Uh, if it if we try and relate this back to epidemiology, right? We are roughly 7 billion plus individual people inhabiting this planet. And then there are, I don't know how many these individual virus they are present at this point in time. So basically, each of this virus individual is interacting with individual people on this planet, and each one of us has a different physiology. The individual interactions are different. We cannot understand all of these interactions at a granular level. And it's not just how this interaction happens with one person, but where this person is placed, what geography this person belongs to, what is the neighborhood, what is the climatic conditions, and all these things together, which is scale and diversity, they come hand in hand, and that decides how the disease will spread, how this virus will go on from one person to another person, one state to another state, one country to another country, and so on. So that is one part which makes it a part of a complex system. Moving on, the second characteristic of a complex system is network. All of us are so closely connected. Right now, we are connected virtually, but in a normal world before COVID, and even right now, we are as well connected physically. We go out for shopping, we go out to buy groceries, we go out to buy essentials. There are certain interventions like lockdown which are meant to reduce our interactions and then create a more sparser networks. But again, it is difficult to understand how these networks are structured globally. And these networks, since they are complex, it's another yet important characteristic of a complexity. Then next thing comes, which is non-linearity. I believe all of us must have heard this quote, "Flap of a butterfly wing can change the global climate." So basically, if we want to visualize this in terms of epidemiology, what it means is, so currently number of exposed individuals or number of infected individuals, and if we see the number of people who will get hospitalized, and if we try to come up with a relationship, it will not strictly be linear. There would be so many factors which will define that the relationship will change. It can go like polynomial or it can even subsidize. But we need to understand it in more granularity. We cannot say that in number of individuals who have been exposed right now will always get into will need medical attention and will be hospitalized. These relationships are quite complex. Basically, we need to know if the individual has any comorbidities, what is the immunity level, what has been specific diet this person is taking, if it has any impact on the spread of disease, and these kind of things that will define what will happen. Then fourth most important thing is emergence. What happens is all of this complexity is emerging from micro level and it is causing some macro level effect. So there are individual people who are interacting with each other at a day-to-day, like the normal routine life. They have been behaving similar, and now since there enters one person who is infected or the person who is carrying a virus, it starts creating patterns. People have been interacting, and these interactions are spreading the virus across the board. And that means micro level interactions are causing an effect which can be seen at a macro level. And we need to understand that as well. So that is where the study of epidemiology becomes a part of a complex system. Uh, Now then question is, how do we understand and how do we study these complex systems? As we have already established that these things are not definitely easy to understand. We cannot say if today there are 100,000 people who are infected, tomorrow it's gonna subsidize, or day after tomorrow it's gonna increase. We need to come up with some understanding of it. And specifically in this case, what we'll be talking about is one such tool or one such discipline which can help us to understand the spread of epidemic, and we call it as modeling and simulation. So basically, what is modeling? Is it something new? Has it been introduced recently? Actually, if we try and think, right, all of us have been doing this quite a long period of time. We have been building our own mental models. As simple as imagine that I'm staying at a point A, and now I want to go to office, which is at a point B. I know the distance is 10 kilometers, and if I start now, I might take 15 minutes to reach, for an example. So what I'm doing, I'm creating my mental model. Now imagine that if I start in a rush hour, imagine it's 9:30 in the morning, and I start from my home, then I need to accommodate, okay, because it's 9:30, it's rush hour, there might be a lot more traffic than I expect. So basically what I am doing, I'm creating my mental model, and at the same time, I'm simulating, I'm visualizing and how will I go to office. Imagine there's a festival and I know a certain road would be blocked. Then I would again going back to my mental model and feeding this data. It says, okay, XYZ road would be blocked. What it means, I might need to take a detour. And if I take a detour, essentially it's gonna add 10 minutes of time. I'm again feeding that data to my mental model. And that is how basically modeling and simulation works. So what are the different types of models we have? So if we look at this slide, right, on the very left, we have a chess. So what chess depicts, chess can be visualized as a minimalist model of a war. Basically, people have been studying chess and people have been playing games like chess to understand how war can be fought. Is it easy? Does it mean that chess will encompass all the complexity of a war? Definitely no. But can it still be useful to come up with certain strategies which can tell us what we can do if we want to tackle a specific situation? Definitely. Then chess is kind of too simplistic to visualize, to build a model around. But then we have been playing these Age of Empires kind of virtual games, right? Which are again can be seen as war visualizations. Basically, in Age of Empires, we create the entire civilization, and then there would be another enemy civilization, and we will be trading. Then we'll have simulations with our friends, and then we'll be trading. We'll be creating an armies, and then creating a war kind of a simulation. Uh, on the similar side, we have these on the ground military simulations. So militaries of multiple countries, they come together and in a friendly way, they simulate a war kind of an environment. Because if there's a war kind of situation, uh, every individual has to go through a different mindset. And to cope up with that, we need to keep practicing. And this can be seen as one way of those kind of simulations. So basically, model is nothing but a representation of a system. And what is simulation? Simulation is nothing but that system in action. Basically, when we put the system in action, it starts imitating its behavior and we observe what is happening. That is known as simulation. Uh, there are multiple types of simulations. If we want to categorize, we can think of what if, what, and random events. We'll see what these simulations mean. Then briefly talking about another, a more detailed way of looking at simulations is, or models specifically, is there can be physical and virtual models. We have spoken about these like chase. If we want to imagine, if we want to build a dam, which can be constructed out of actual physical material and can be tested against, say, X amount of rain, will this dam withstand with this? So that will be simulation on a physical model. Similarly, we can create a virtual model of a dam, and then we can create a virtual ring and see how this dam can withstand. And then going in detail, right, there are multiple different ways of even creating these virtual models. This is a famous quote from George Fox, who was a statistician, and he said, all models are wrong, some of them are useful. So let's see what it means. Uh, I believe we have already spoken about this, right? Basically, we build a mental model, then we put this model into simulation, then we try and create some computational model out of it because we want to run and understand characteristics not over one incident, but over multiple incidents, over a scale, over multiple phenomena. So imagine that in this case, right? If I'm someone like an epidemiologist and I build a mental model which says if I put a lockdown, it should benefit me. So that is my mental model. Now, can I actually put a lockdown in actual population and see? It would be too difficult because it's an experimentation. And these experimentations, they come at a cost. When we say lockdown, right, it means an impact on economy. And we cannot always handle these kind of impacts. So can I test it in some sandbox environment? So that is where this computer simulation comes into picture. Now, what I will do, I will generate a population, then I will try and place them under the lockdown, and then try and understand what it means if there is a lockdown. Then once I have results, I will put back into my mental model and see. I was expecting, okay, if there is a complete lockdown, the disease should subsidize with this factor X. Did it actually subsidize? Yes or no? If yes, then what might have caused it? No, what might have this reason? So basically, I'm again training my mental model. And then I'm putting my understanding back into my computational model, and this process continues over and over. Uh, Till now, how epidemiology has been studied or how the spread of disease has been studied, there is a famous groups of models which have been called as compartmental models. So in these compartmental models, imagine that the entire population has been split into three exhaustive compartments, which are mutually exclusive as well: susceptibles, infectious, and recovered. It's popularly known as SIR compartments. So all the healthy individuals gets into susceptible compartments. All the infected individuals are part of infectious, and all the individuals who have recovered or deceased can be seen as the last compartment, which is recovered or removed. What people have been doing is they have been running these simulations with differential equations. We would have heard a lot when COVID itself started, right? There's a R naught, we need to reduce the R naught. Then there is some beta, which is infection rate, gamma, which is rate of recovery. Now these parameters, they can be studied, and once we have these parameters with us, we can create a computational model or a model which is based on calculus, and then run it again and again and see how it behaves. Basically, we can tweak these betas and gammas and alphas and all such parameters and see what impact it creates on a graph, on a population. So basically, that has been the way earlier to study these epidemics. But there are multiple limitations of these epidemics, of this continuous or calculus-based methods. Because these methods are, it's technically not infeasible, but it is too challenging to understand how can we model the real-life complexity. So basically, when we say complexity, right, one example I gave is comorbidities. Now, even the infection rate is some X or some beta, for an every individual, this rate would mean differently based on the multiple habits of these individuals or multiple characteristics of this individual. When we simulate for city A against when we simulate for city B, both the cities might have different population density. And based on these details, again, the spread of disease will differ. And it will be too difficult to model all of these complexities into such calculus-based methods. Then another important thing is these partial differential equations or differential equations, they are with respect to time, and time is continuous. But in this case, what we are trying to do is we are trying to simulate a model which is discrete in nature. We need an ability to stop a simulation in between and say, okay, look, I have got certain number of vaccines. Can I put these vaccines into this simulation? What will be the impact? Uh, Now we need to place a lockdown. Can I start my lockdown at a specific tick of a clock and then see what happens to my simulation? So modeling these kind of things actually become more and more difficult with calculus-based methods. Uh, and then the last important thing which we saw earlier as part of complexity, right? There's this phenomenon of emergence. Individuals, they are interacting at their own level, at a micro level. And these micro level interactions are causing effect which can be at a macro level. But with these partial differential equations, there is no concept of emergence. So that is where we need to look for alternatives. And one such alternative which we have is agent-based modeling. So basically, what is an agent-based model? If we can visualize it, it is a stack. It has multiple layers in it. Basically, let's try and break down this agent-based model in the context of epidemiology. So as we earlier spoke, right, spread of cases might as well be functional the geography, how the residents are spread across the specific geography which we are trying to study. Where are the workplaces located? How people are commuting from their homes to offices? Where are the markets? What is the frequency of people visiting markets? Where are the hospitals? Who are the hospital staff workers? At the same time, so this is about geography. Then on top of it, there is a layer which talks about disease dynamics. So what is the infection period? Once person is infected, how long it takes to get that infection out of this human's individual's body? What is the severity percentage? If 100 people catches on disease, how many might need the ventilator kind of facilities? How many people might need oxygen and oxygen beds? What is the death percentage in case of this specific pandemic? So these details, we need to capture them at a disease level. Then one of the most important aspect comes into picture, which is synthetic population. As we spoke earlier, right? All of these viruses, they interact with every individual human differently, and these would be characteristics of every individual human. Might be because of blood group, comorbidities, what is the age group, uh, what are their mobility patterns, how they behave, and then even human behavior comes into picture. So that layer can be uh, briefly captured as synthetic population. We'll revisit the concept of what makes the population synthetic. And then we have interventions. Because there's this trade-off, this is ongoing, it means someone has to intervene. someone has to come up with strategies to fight with it. So we have been seeing these vaccination, lockdown, social distancing measures being in place. Then government is trying to increase the number of beds so that we can accommodate more infected individuals and can treat them better. So in this kind of agent-based models, we try and model each and every entity which is of our interest, and we can call it as an individual agent. This agent will have their own characteristics, and based on these characteristics, they will start behaving. So I'll just briefly talk about examples of geography which we have been dealing with. So on the left, right, we can see it's kind of a network-based geography. So if there are two individuals who are living in the same house, we can think everyone as a node, even the individuals and a house. Then there's a relationship between these two individuals, seeing they are located in the same house, and then they will have relationship with house, which is uh, this house is hosting these individuals. Similarly, there would be nodes for office, school, and so on. On the right-hand side, we see another way of modeling this geography, which is a minimalist model. As we saw chess, right? Chess cannot be exactly imitate the behavior of war, but still is a useful model of a war. So similarly, on the right, we see grid-based geography. Where we have dedicated home areas, then we have transport, work areas, and hospitals. And then there are these dots which we can see, those are nothing but individuals. And then these individuals will start interacting once we start the simulation, and that will lead to generation of certain patterns. Uh, as well, we spoke about another layer, which is disease dynamics. So as we know, now the disease has been split into multiple compartments. So there are susceptibles, exposed, infected, recovered, and disease, right? A model can even be more complex. One such example is there will not be just one compartment for infected, but we know in terms of COVID, right? Infected are different categories. We know most of the population is infected but asymptomatic. They do not show any symptoms. On the other hand, there are infected which are symptomatic. Again, in symptomatic, there can be multiple ways. There can be mild symptomatic as well. There can be severe symptomatic. Going ahead, these severe symptomatic, they might need hospitalization. So all of these states of population who are uh, infected or who are dealing with these diseases can be part of one such compartment. Then, as we have been speaking about agent behavior, so every individual in this population would still have their own routines. No matter if there is a lockdown or not, they still need to continue with some level of routine and they still need some schedule with them. So basically, the population might be divided into people who are employees who are working with someone, and there might be students. There might be some fraction of population who are homebound, who are not going out, but still they are doing their day-to-day activities. Then how do these agents they commute? Basically, imagine that people who are going to office, are they taking public transport? Are they taking their own cars to office? Are they taking two-wheelers? What about students? How they're commuting to office? Uh, then when it comes to interventions, right, as we spoke, not everyone takes the intervention at the similar way. Uh, People respond differently to different interventions. Not everyone is comfortable wearing a mask. Then there would be some fraction of people, even though imagine there is a lockdown, not everyone will comply fully, but there might still be some fraction of population who will defy the lockdown. Uh, in this set of agents, there might be certain people who are essential workers. What we mean when we say essential workers, imagine they are medical staff, imagine they are doctors, imagine they are working with municipal corporations. So no matter what level of pandemic we have been facing, they still need to go back to work. So we need an ability to model these various complexities when we speak about this population. And then we already spoke about interventions like vaccination. But then there are different complexities which comes into picture when we speak about these interventions. Uh, Basically, imagine when we speak about vaccination, right? When to start vaccination? Whom should we start vaccinating? Should we do age stratification? Imagine, should we start vaccinating people who are above age of 60 plus? Then should we go with 45 to 60? What should be that strategy? Uh, do we know how many vaccines are already ready? Those kind of questions that would need answers. Then similarly, when we speak about lockdowns, should there be a partial lockdown? Should we expect people to work every alternative, or should we have a complete lockdown? What it means when we place a lockdown, what will the impact on economy and what not? So these kind of questions, right? We still need answers for. So that is roughly what sums up the problem. And now let's see how we have been trying to solve these questions. We have two different ways which we tried and look at this. So we have one application or a configurable application which we call as EpiRust, and other framework which we recently built, we call it BharatSim. So EpiRust is epidemiological simulation written in a Rust language. That's why we call it EpiRust. And other one is BharatSim. But let's go one by one and have a look at it. Uh, Before we talk about these our attempts to model these pandemics, right? Let us understand one more thing. We have talked about domain complexity till now. Basically, we did know how it is difficult to model an epidemic or a pandemic. So we know domain complexity, but it's not just the only complexity, but there are multiple levels of complexities. So once we understand the domain, it is difficult or it is complex enough to again put this complex domain into computational model. Once we have our computational model ready, which means we again need to create a software implementation of the same. And even when we create a software implementation, there can always be ad hoc complexities, which can be playing their own role in this implementation. So let's briefly talk about what is EpiRust. So as I spoke earlier, right, roughly somewhat October 20 or a bit earlier, we started with creating EpiRust. So EpiRust is minimalist approach at looking at this disease modeling. So we have a grid-based geography. Image might be a bit difficult to visualize, but there are grids and there are locations which are like 2x2 location can be seen as a one home, and each blue dot is an susceptible individual. Then there's this round dot which can be seen as an infected individual. And then once the simulation starts, every individual will start moving. They will go through transport section, then they will go to their respective work areas, then they will interact with each other, and basically it will generate spread of a disease, and that can be visualized on the right-hand side as a SIR curve. So we can see there's this susceptibles which are decreasing over time. Then the infected and exposed are picking up along with the people who are getting recovered. This is again, we can visualize it as we had seen earlier in the SIR model with calculus-based approaches as well. So what is special with EpiRust? EpiRust is an open source application. It is quite configurable. When I say configurable, it can handle variety of diseases. So actually, when we started some part of it even before COVID breakout started. We were trying to understand how SARS and MERS kind of diseases can be simulated. So basically, that is where this EpiRust can cater to a category of or a group of diseases, and it's more of like configuration driven. So if someone changes parameters in a configuration file, can see impact of a different disease on the population. Uh, One biggest stronghold of EpiRust is it's the scale and the performance which it has. With EpiRust, we can simulate a city kind of a population, which is roughly up to say 5 million. And we can run a simulation on this 5 million, which is in matters of 2 or 3 hours based on the model complexity. But EpiRust does not stop here, it can scale out. So when we say EpiRust can scale out, it means we can spawn multiple such engines or multiple such instances of city, and each of this city instance can run on its own. And then potentially it means we can even simulate 100 million population across multiple cities in a matter of 5 to 6 hours or so. And is it that all these cities are independent? There is no impact. That's not the case. With EpiRust, we can actually model certain problems as in human behavior. So what happens is, if disease starts in a city A, there might be a fraction of people who will try and migrate to city B. Again, some part of this fraction might actually be carrying infection with them to the city B. And with this EpiRust in place, we can actually model these kind of migrations and what it means to have these migrations over a spread of disease altogether. Uh, as we said, we have quite a flexibility about how do we define the geography, what is the disease dynamics, and how should we intervene in this disease model. Along with it, EpiRust has its own visualization tool as well. So we started with EpiRust, but we again, while thinking about it, right, We started building EpiRust more as an application. We always had configurability back of our head, but when actually this COVID-19 pandemic started, right, the kind of questions which were being asked, there was so much complexity, and it was difficult to incorporate all of this complexity on the go. So basically, I'll tell one such scenario that we are trying to create EpiRust, and then government here in Pune, where I'm based off, uh, started with a different thought. So what they started differentiating between localities. So there might be a red zone, green zone, amber zone, which will be talking about level of infection in this zone. Then we started thinking, okay, can we accommodate that? We started accommodating that. Then government changed the policy. Now they had micro containment zones, basically, which means now not the entire neighborhood or the block will be under lockdown, but there would be a society or individual building or a street which will be closed. So then we started trying that. But then we sooner felt that, okay, as the condition outside changes, it is difficult to keep evolving this model since it has been built with configurability in mind, but not enough flexible. And that is when we, along with Professor Gautam Menon from Ashoka University, who is a renowned epidemiologist in India and around the globe, we started collaboration. This collaboration, we called it BharatSim, and which is funded by Bill and Melinda Gates Foundation. So what is the vision for BharatSim? Vision for BharatSim is to build agent-based framework at a scale and complexity of Indian population. So we, even though we call it BharatSim, it is not strictly tightly coupled with India, but I will say where the BharatSim comes into picture. But the biggest thing which we felt is there are far less such simulation frameworks which can tackle the scale or complexity which is there in the Indian environment. So what are different features of BharatSim? BharatSim is scalable. So we can write models which are for 10,000 people to 100,000, even to people or even to population, which can run to million or 10 million or 20 million and so. It is flexible because BharatSim has been created as a framework and not as an configurable application. I'll briefly talk about what it means that we are creating a framework and EpiRust is not a framework. To some extent, BharatSim is still work in progress, but soon it will be contributed to open source. And one key factor which BharatSim has, it's a synthetic population. So what is synthetic population? Basically, we know that every individual in a population is different. And the way this disease interacts with every individual is different. But we do not have all of that data. That data might be published as part of surveys, or sometimes we just get percentages, which says, imagine that uh, in India, there's X percent of people who are literate against Y percent of people who are illiterate. What is the gender diversity? What is the ratio of gender diversity within India or within a city which we are studying? What are different age distributions? How many? What is the fraction of population which is between the age 0 to 10 to 10 to 20 against 80 to 90 or beyond 90? So all of these numbers, they are typically published as fractions or percentages. But what we need is we need to synthesize this data and then come up with much more granular details. And potentially we should be able to create a population. Imagine if we are talking about Pune city, which has 3 million of population. So can we create 3 million records? We may not be able to name these individuals. We may not be able to pinpoint the exact address, but this population should more or less be able to capture the dynamics which is happening or which is going in this specific population in the specific city. And then at the same time, it's not just a synthetic population, but the modeler, the person who is writing the model, needs to capture the behavior of intrinsic behavior of this particular place or of this particular city. So even it's not just a synthetic population which will differ city to city, but might even be the way a model will be written. So these two things essentially becomes the input. So we started building our collaborators, Ashoka University, they started building this synthetic population. We started building the framework which will be consuming this, along with a model which will be sitting on top of this synthetic population. So does that mean this BharatSim framework is strictly tightly coupled to India? No, right? If we get a population for different city and if someone can mimic the behavior or predict the behavior of individuals in that city, we can very well accommodate this for different cities or different countries for that matter. So who will be the users of this? Because it's a framework now, right? It's not an application, which means now someone has to think about a model. Someone has to capture the gist of behavior of individuals of this population and then put it in and then start the simulation. So basically, BharatSim is targeted towards researchers, people who are trying to understand the phenomenon. So what we expect them to either consume a synthetic population, build their own synthetic population, create a model, then run simulations. It is as well targeted for academic advisors who might be dealing with multiple researchers. They can collect the data, they can collect the output, visualize it, and then uh, try and create some output which can be input to policymakers. This can as well be used by policymakers to run multiple simulations and try and train the mental model, as we spoke earlier. So basically, how BharatSim has been structured. We already spoke that synthetic population becomes the input to BharatSim. Then on top of this synthetic population, there would be a user-defined model. Then all of this would be fed into simulation engine, which will churn out, which will understand the notion of agents, which will understand the notion of behavior, understand the notion of schedule, interventions. And it will put all of these complexities together and run this model for multiple ticks, for multiple time intervals. And once it is through, it will generate some output, which can later be visualized using a visualization dashboard. So soon we'll go and have a look at demo of this BharatSim engine. So what are different abilities this has? We have already spoken it. There are four crucial parts to an agent-based model. And these are not exhaustive, but essential parts. We know there's a geography, there's disease dynamics, there are agents, and then there are interventions. So this BharatSim frameworks give certain capabilities as how to define agents, what should be the agent parameters, what is the social network or contact network, which is around these all of these individual agents. So basically, how two people are connected? Is it the first connection or second connection? What is the time that these two individuals will come in close contact? Imagine that there are two people who are staying in two different houses, but they are working in the same office and they are colleagues. So imagine in work hours only, these people will be interacting with each other. Once both of these individuals are back at home, they will be interacting with their family members. So how can we capture these interactions? Then what will be the schedule? How will these people be commuting to their workplaces? Will it be public transport? Will it be private vehicles and so on? Then basically we need a way to accept the synthetic population, right? Because synthetic population more or less will define how the model will work. So basically right now we have a way to read a CSV file, which will have the synthetic population captured. Then the simulation engine offers a way of defining these business dynamics, defining different types of interventions, and then there would be some certain actions which modeler or model developer might be interested in knowing at each tick or each simulation unit. That tick might represent 1 day, that simulation tick might represent 12 hours, or it can very well represent 1 hour. Again, it is open for model developers, how model developer envisions this particular model. I'll briefly stop here and then we'll share my entire screen so that I can demo. Hope my screen is visible. This is not actual synthetic population, but look at this as a dummy data, which I'll be using for this particular run. So basically, there are agent IDs and there are age, then public transport drops. Again, do this for people take public transport or not? Is the individual an essential worker and so on, right? What is the latitude and longitude of this individual's home? What is the home ID? What is the workplace ID and so on? This can become very complex. The ones which we are dealing can have 20 to 30 or even n number of columns. When I speak about simulation engine, right now it is in terms of a code. Basically, whatever written under this model directory can be visualized as a model, which has been written by model developer. And basically, what model developer is saying, model developer is talking about from where to read the population, what will be actions, how the schedule of this population will be, what will be the actions I need to perform, other interventions, what should be the interventions, how my disease is structured, and so on. So basically, along with this, model developer as well as defining disease characteristics, population characteristics, and so on. So once I run this, right, it is reading the same synthetic population as I showed. Now the application will start running. And once it starts running, it will show certain log, which is vertic action. We do not need to worry about what is happening underneath right now. But basically, what it will be doing, it actually at this point in time, simulation engine will kick in. The framework will start interpreting these individuals. The framework will start putting these people on certain geographies. Then simulation will start moving these people around, then churning out and then recording, registering certain events. What is happening? What is the count of infected when the simulation started? What is the count of infected after 10 days? What is the count of infected after 15 days? And so on. So let's see once it starts into action. Yeah, now actually the simulation started. For example, I'm using a population with 10,000 people. That roughly should take 30 odd minutes, 30 odd seconds to finish. So by looking at this log, now we see in this model, specific model, we have 12 hours a tick. So if you are at tick number 20, which means the simulation has completed 10 days of running. So meanwhile, this is running. I already have one sample output which is generated. I can show that on a visualization engine. So this is the other part of this BharatSim framework. It allows us to visualize what is happening around. So as I said earlier, it generates the data in terms of a CSV file. So it allows user to upload the CSV files. Okay, I believe I did not use the right file. Yeah, better I use the file which will actually be generated. And then later we can talk about some of the runs, results of some of the runs which I had carried out earlier. Let us maybe give like half a minute for this and then let's finish. Meanwhile, do post if there are any questions. Okay, now it is done. Now if we see even here, right, it is putting some numbers, but better let's see it in action. And the application earlier crashed because I'm running it in development mode, but it will not be the case when we'll actually go into production mode. Yeah, the file has been uploaded. The name might start with something SIR graph. Now we know what SIR is. And I'm just plotting susceptibles, exposed, infected, and recovered as part of the population. And then they should create certain kind of curves, which we can use to understand it more quickly. So I have already ran a couple of simulations and I can walk you through what we have. So basically the simulation, again, the simulation was ran with 3 million of population. So if we look at this graph, right, what it says is once the simulation starts, we had some initial condition. We started with roughly about point not 1% of the population being infected initially. So if we say out of 3 million, again, this is dummy sample run. At one point in time, active cases were roughly about 500,000. And we ran the similar simulation with intervention in place. In this case, we used intervention, which is lockdown. So basically, we started lockdown when actually 5% of the population was infected. Lockdown was placed for a month. And now if we see these results, right, in earlier simulation, the peak was at 1 million. So basically, 30% of the population was infected at max. And if we see in this case, the peak has been subsidized a lot. It has been potentially 70% of what it was earlier. And this is with dummy data sample then. Once we get more complex data, once we have better understanding about these parameters, we can run these simulations with much more granular understanding, and from which we can derive multiple insights. So one such insight which we can see out of this is lockdown actually works. Lockdown helps us to flatten the curve. But what should be the period? We can actually try and run it right now. We ran it with 30 days lockdown, right? We can try and run it differently, say 15 days, and then see what is the impact. How much impact will be if I run it with 60 days, and so on. So we'll get an ability to ask such an interesting questions, which otherwise is not possible with calculus-based models. So is it that only epidemiology is a domain where this modeling and simulation as a discipline can be applied? So that's not the case, right? People have been exploring for quite some time, and the specific framework, which is modeling and simulation, it can be used along with multiple different disciplines and domains at the same time. So this has been work of these two amazing teams, EpiRust and BharatSim. Many of the folks have been working common in both the teams. Yeah, and with that, we are through the presentation, and we are open for questions.
Thanks so much, Jayanta and Praveen. Praveen has answered some questions in the chat, I see, and we have two that haven't been answered, and I can read those out. So PG has written, okay for butterflies and storms, but do the exact initial locations of the agents matter a lot to the outcomes?
Well, depends, right? Basically, what happens is there are two things. What kind of model we have? If we have model which is across millions of people, we might see impact of normal distribution taking in place, right? It's like, but at the same time, if we can identify the infection in early stage, imagine that the infection starts from a place which is not densely crowded. What it means is, in that case, the infection might start spreading a little slower. But imagine if it starts in a place which is quite densely crowded, then it can take a different shape altogether. So basically, it is about how do we see what kind of granularity which we can model. That will play a big role in these kind of simulations. But will the matter of, say, a person who is surrounded by 20 individuals and then a person who is surrounded by 19 individuals, and if we start the simulation with these two initial conditions, the end simulation result may not be drastically different, because again, we are running it over a period of time, over potentially 100,000 or million agents as such.
Yeah, I'll just add on to that the point which Jayanta said. On a different note, this home locations or work locations does matter to the policy making point of view. Just to see and analyze the results, and then the visualization tool, how exactly and how dense the current situation in any particular area is looking like. And based on that, there are various decisions or the interventions that anyone from the government policy making point of view would like to make.
Thank you to you both. We have another question from Angshuman. I'm sorry if I mispronounce your name. But your question is, recently there was an article criticizing India's supermodel, and one of the reasons cited were only 4 parameters considered, which further was broken into 6 stage or phase, enchanting for 24 parameters in total. How do we stand with that? Have we done any city-based modeling, and can provide any indication on parameters or predictions?
That's quite a nice question, actually. Basically, this talks about complexity of a model. So imagine that what will be the most ideal case if I can accommodate all the complexity which lies outside, right, as part of my simulation model. But if we could do that, what it means is now we are equally clueless. We can individually observe what is happening outside. We'll observe similar behavior within the model. And at the same time, it has compute complexity, as we saw that sphere of complexities, right? When we run this model, actually it takes good amount of time as we go on adding complexity. So basically, how should we define the parameters? for a specific model? I guess the answer lies with what kind of question which we are trying to ask. So imagine that me as an individual, if I'm interested in knowing what is the impact of COVID-19 surge on the healthcare system? How do I need to scale this healthcare system so that I can accommodate infected individuals better? In this case, I would be interested in knowing what is the maximum number of infected people who would need severe attention. What fraction of the population will need oxygen beds? What fraction might need ventilators, and so on. But if I'm looking at the same COVID-19 disease as a crisis from a different perspective, imagine from an economy perspective, then the set of parameters which I model would be different. So essentially, and keeping all the complexity in one model actually makes reduces our ability to understand the impact. And even this relationship is not linear because all of this is quite complex. Added one complexity as another dimension, and it creates another number of possibilities. So I may not be actually exactly be able to comment on the Indian supermodel, but at least the way we look at choosing parameters is based on the question and what it is important, what are the important parameters which can lead us to the answer of this particular question.
Thank you. All right, we have another question from Ram Prasad. This is amazing work. I wonder what kind of power it might mean to be able to factor in geopolitical phenomena, undesirable pockets of swarm behavior of people within a state or city due to events like elections, natural calamity, festivals, etc.
Definitely. So basically, even in India, right, we observed one such phenomenon that when the first COVID-19 wave started, many people started migrating. They started moving from cities which were infected largely and then going to rural places where they actually belong. This was mainly the working class population. Now, all of these interactions, right, and this can as well be seen as human behavior. And this migration actually means something. So we as well have an ability to model such a behavior. Along with large case gatherings, then we can even accommodate to a bit simpler phenomena like marketplaces or even gardens. Imagine that a bunch of people are actually visiting gardens over weekends. Even those things can be factored into these agent-based models.
Yeah, just adding to that, the one very important point when we add more complexity into our model is that you need to analyze with what if scenarios or if what scenarios, and that gives you better analysis as well as power while you build the model. If you keep different complexities or the different parameters included into the model at one point of time, it is very hard to predict or judge that what exactly has happened to my outcome and because of which parameter it has been changed. So it is very important that when you try to build the model, or even when you try to computationally build the model in your brain, you try to analyze it with one kind of scenario and try to judge the outcomes based on that particular scenario.
Thank you both very much. We have another question from Abhishek. Would it be possible in the future to ingest a real-time stream of data about the population instead of a CSV, say from a camera feed or from election voting numbers, and then scaling it up as needed?
Yeah, that's actually an interesting question. So frankly, we haven't thought through this yet. Basically, right now, our thoughts that it's the representation need not just be CSV, right? It can be any static data in nature to begin with. But the thought is quite nice that if my data as well is changing, if my population is changing, what it means for my simulation. On the surface, seems feasible, but I'm still trying to digest the fact that, okay, I started my simulation with 100 agents, and now suddenly, because I'm reading it from the screen, my agent has been gone to 1,000. Technically feasible. What will it mean in terms of domain is still trying to understand.
Thank you. Right now, I think you've answered the questions that have come in the chat. So everyone, if you do have questions, we still have some time for these to be addressed. I'm just gonna ping into the chat now info about the upcoming sessions. So I'll do a little promotion while we're waiting for more questions. I hope that's okay. But as you know, the Engineering for Research meetup series has a few more events. So we have the next session will be coming up on June 10th and so on. So you can find the information there. And I'll just, again, if you have questions, now's a great time to share them. I just want to thank so much Jayanta and Praveen for presenting today, all this your fantastic work. And I don't know if you have any, while we're waiting for questions, if there's anything you wanted to share about the project or in general, just as kind of a closing thought.
Jenna, there is a question in the chat.
Great.
From Romel.
Ramel. Okay, I'll read this out for the sake of the recording. So this is brilliant, Janta and Praveen. Data-driven economies, predictive healthcare infra, the options are endless. Well done with that. But with all things data, there comes privacy concerns. What are your thoughts?
Yes, Roman. And in this case, right, the data which we are using, basically we are creating a synthetic population, which is from the published surveys. So the surveys have been conducted by multiple authorities at multiple levels, and we are creating synthetic population. One good thing about the synthetic population is we cannot pinpoint an individual in this specific population because this is all anonymous. It is obfuscated. We cannot pinpoint an individual with the name XYZ in this. There are no names. Even though we are dealing with lat-longs, even we are trying to model houses, but these may not be actual homes. These are addresses which we have generated, and in terms of latitude, longitude. But can this synthetic population be used for multiple different purposes? Yes, it can be. But what we are trying to model is something which is an outcome of one's thoughts, one's mental model, and the individual who created the model is the best person to talk and to understand these results. And in that case, whatever this person publishes actually becomes the artifact, and not the model, not the population itself. Because as we spoke, right, the question which we are trying to answer, that defines the model, and as well it defines the attributes which one might be interested from synthetic population. Hope that answers your question.
Thank you. I think we might have missed another question to Praveen. It was, you are saying it's still based on the few humans mental model towards a desired outcome?
Yeah, so I just replied back to Anshuman, and that's really the case, that you need to have the very good understanding about the domain. For our case, it's epidemiology, which is understandable to each and everyone in the society for now. But if for tomorrow, if the domain is so complex, like the banking or the finance or the economics, and how is one thing kind of an impact on another thing? For example, if digital currency comes into the picture, how it's going to impact the entire generation or the next set of population? This needs to be understood by building at least the basic simplistic models first. In our case scenario, for epidemiology, it was SIR model, which was very easy to understand and kind of an easy to implement. But when it goes to the different domains and when it goes to the different industries for specific problems, then we need to build the basic models very particularly, and then only we could understand with what if scenarios that if such and such change is going to happen in our system, or if such and such intervention could come into the picture, what is going to be an impact. And that's where it's very important to understand that domain very well.
Thank you. Now, I think we did answer, or you both answered all the questions. So I would say maybe this is the time we could wrap up. So if you have any final remarks, it would be wonderful to hear those. A big thank you to our presenters, Janta and Praveen. Thank you for sharing your insights with us today. And a big thank you to everyone who joined.
Thank you.